Okay, today we're looking at the log graphs. We're saying, and here where it says where a is greater than 1, so the base is greater than 1. So if you have a look here at the different logs, so in the red we have a base of 2, and then e is a natural log and log is a base of 10. So you can see the bigger the number, the base, the narrower it gets like closer to this x-axis. So a basic log graph, so we'll always see the intercept at 1, 0 there. So we see that point to be 1 and 0. And we also see this asymptote on the y-axis. So we see this y-axis and the graph goes close to it but never touches it, so it asymptotes on x equals 0. So that's a log graph. Now if you look at an exponential graph, so looking down here on the bottom graph, we see we've done log 10 of x in purple. Now if you look at 10 to the power of x, we see, which is an exponential graph, we actually see it's a reflection in the red line, the y equals x. So when we have a reflection on that, that's actually inverse. So we can see the inverse. So looking at the purple, the log graph, if we looked at the domain, so what values x can take on, we can see x takes on all the positive values of x. So that's why we said real field positive. And the range is any number, it's going all the way negative, all the way up to positive. So that's being any number, so it's the real field. Remember when we did the inverse, the domain and range swap. So up here you see that the domain of the 10 to the power of x is actually the real field, the same as that one, and the range is just real plus, so it's done the inverse. So if we go on and do a couple of examples for our log graph, so we're probably going to talk about our transformations here now. So if you look at this -2, that is going to move the graph move the graph down 2. And if we look at this +1, that will move the graph to the left by 1 unit. So we've done all this in translation, so we know how that these things move the graph. Alright, so if I was to draw the basic log graph, we know it would look like that. So I'm just drawing the basic. That would just be log 2 of x. So if you look now, we're going to move it to the left by 1 and also down by 2. So if we're moving it to the left by 1, our asymptote has moved over from x equals 0 to x equals -1. So we're going to see our graph asymptote on that. And we'll also see it move down as well. So we probably want to find the x and y intercepts of this. So remember the x-intercept is when y equals 0. So off we go. So we have 0 equals log 2x plus 1 minus 2. And I'm just going to keep rearranging this. So I've put the 2 on the other side. And now we can use our exponential or log law. We know if it's a base of 2 and we say equals that, equals the x plus 1. So I can say 4 equals x plus 1. So 4 minus 1 equals x. So 3 equals x. So our x-intercept is at 3. So if I was going to draw this graph here's my x-intercept at 3 and 0. And if I go about... Okay, so let's go find the y-intercept as well, which we know is when x equals 0. So if we we've got the formula, so y equals log 2. Now we're putting 0 in there, 0 plus 1 and then minus 2. So we end up with y equals log 2, 1 minus 2. So what we're going to do is we're going to find out what log 2, 1 is. So then we can work that out. So if I look log 2, 1, and let's say we let it equal x. This is me trying to solve what log 2, 1 is. So we can say 2 to the power of x equals 1, and we know to get something to the power of, or to get it to 1 if we raise it to the power of 0. So we know x equals 0. So we know that this bit is equal to 0. So when we find out the y-intercept is 0 minus 2. So y-intercept is minus 2. So we see down here, here's our 0 minus 2 y-intercept. So we've got, down here. So if we go and draw our graph, it asymptotes and looks something like that. It's a really bad graph. Make sure you do better than that. Okay, so that's that one. Okay, let's have a look at this log graph. So because this negative here reflects the graph in we're making the whole function negative, so it reflects it in the x-axis. But this negative here reflects it in the y-axis, so we're doing a double reflection for this one. So if you think about the graph will reflect, so we'll think about that later, but we might find the x and y-intercept. So the y-intercept is when x equals 0, so we have y equals 2 minus log 2, 1, okay, and we saw log 2, 1 before was equal to 0, so I'm just going to say y equals 2, so we know the intercept is 0, 2, so I've got that one there, 0, 2, and if we do the x-intercept, that's when y equals 0, so we've got 0 equals 2 minus 3 log 2, 1 minus x. So we'll bring the 2 over, it'll be negative 2 equals negative 3 log 2, 1 minus x. I'm going to bring the 3, it's timesing, so it'll divide. Log 2, 1 minus x. So I've got 2 over 3 equals log 2 to 1 minus x. So I'll change that to that exponential rule. So base of 2 to the power of 2 over 3 equals 1 minus x. So this one we'll roughly do on our calculator, and we get that 0.59 equals x. So, I'm sorry, negative. And so we see it roughly over here. And now, okay, if we think of a basic log graph, it looked like this first. So if we reflect it in the x-axis, it would look like this. And then if we reflected that in the y-axis, we will get something like this. Now, we have to think about the new asymptote. Now over here, if I factorize that and I actually write negative 1 outside, I would actually get negative 1 plus x, negative 1 plus x. So the asymptote has actually moved to the right by 1. So then we've got this new asymptote for our graph. So I'll just draw that down there like that. So it's actually on x equals 1. And I've got the 2 points there. So I'm just going to draw the actual graph in red. But remember we got this shape here, but we're asymptoting on there. So it does something like that. Oh, that's pretty bad, sorry. But it does this shape. And there. Sorry, guys. Okay, with these final questions, we're going to be asked to find the inverse. So remember we let y equal x. So if we do that, we would have x equals 2 to the power of y plus 3. So bring the 3 over because we're trying to solve for y. And then we can use our log rules because we know that y equals, because you can say the power, log base 2 and the answer here, so x minus 3. So that's the inverse function. So you might say the inverse function of x equals log 2x minus 3. Now, if they asked you to state the domain and range, you need to just have a think about what this graph looks like. So the asymptote's moved over to x equals 3, and so we've got a graph like that. So the x domain would be anything greater than 3, infinity, and the range is all real numbers. So you go real numbers if you have to state that as well. Alright, so let's do the next one. So we're going to let x equal y, so that'd be x equals log 2 y minus 2. So we can rearrange that first. I'm going to say 2 to the power of x equals y minus 2. Sorry, I've run out of room. So 2 to the power of x plus 2 equals y. So there I've got the formula, or I could write the inverse function of x is 2 to the power of x plus 2. So if you were thinking of this graph, just roughly drawing it, so an exponential, remember it's the reflection in the y equals x of a log. So it actually goes like this, but the asymptote, it's moved it up 2. So we've got an asymptote on y equals 2, and it's doing something like that. Sorry, bad graph. So if I think of the domain is actually the real field, and the range can be anything above 2, so 2 and infinity. Alright, and this last one, if we're going to swap it round, so x equals 5 times 2 to the power of y plus 3. So we might bring the 3 over, x minus 3 equals 5 times 2 to the power of y. And then we might bring the 5 over, so that's times in there. Oops, it's dividing here, equals 2y to the power of y, sorry. So then I'll just use the log law where we can say that y equals log 2 base of 2 x minus 3 over 5. Sorry, so inverse function was log 2 x minus 3 over 5. Okay.